Hello, this session is the continuation of the first exercise of the hydrology video tutorial. In the previous video, we added catchments and their runoff infiltration link. We created the land cover classes in the catchments and entered the area and latitude information. We also added a streamflow gauge and saw how to use the remainder 100 function. Now we will enter the climate data to each catchment, create the key assumptions by using a script, and link them to the hydrological parameters. We will run the model and explore the results. Go to WEAP to continue with the exercise. We are going to enter the climate data in the catchments. We will enter precipitation, temperature, humidity, wind speed at 2 meters high, and cloudiness fraction. The cloudiness fraction is also called relative sunshine duration. Do not enter data of cloud fraction. We will enter only information into these variables because the other variables do not influence the results due to the temperature interval in the study area. The freezing point determines which temperature the rain turns to snow. The default value in WEAP is -5 degrees Celsius. The melting point determines when snow is converted to water. The default value in WEAP is 5 degrees Celsius. In this model, the temperature is higher than 19 degrees Celsius, so these processes are not relevant. You must check the temperature range when you are developing hydrological models. The climate data is in the climate folder within the area folder. Go to the WEAP Areas folder, then to SEI Tutorial Hydrology Exercise 1. In the Climate folder, you will find the climate data. Explore the precipitation file. It has daily information, and these columns have precipitation for each catchment. The temperature file has the same structure. The relative humidity file has monthly information, but only for 1 year. The data corresponds to the multi-annual monthly average. We will use the same information every year. We will use the averages in this structure because if we later collect the data for the entire modeling period, it will be easier to include the information in this file. We also have the multi-annual monthly averages for the relative solar duration and wind speed. Go to the precipitation variable for the demand sites and catchments. Access the Read From File wizard for the Catch East. Go to the Climate folder and select the precipitation file. Press Catch. Select the East column for the Catch East. We can verify it at the bottom where we are entering information. In this case, precipitation for the Catch East. We see at the top the full time series graph. Remember, this is daily data and we have a monthly model. That is why we see this drop-down menu to select the aggregation method. Because it is precipitation data, the method must be sum. Finish. Do the same for the other 3 catchments. Carefully select the column for each one. You must have these expressions for precipitation. It is good practice that the names be the same, both in the climate files and in WEAP. East, east, north, north, south, south, west, west. We can see we are using the sum method to aggregate the data. We can do the same for the temperature for the 4 catchments. Use the file temp catch. Because the variable is temperature, the aggregation method must be average. You must have these expressions for temperature. We can see that we are using the average method to aggregate the data. Continue with the relative humidity. Use the file rh-catch. The options in the Read from File window are different. The file has monthly data, and we have a monthly model. We do not need to aggregate the data. Select the East column with the information for this catchment. Because the time series has no information for the entire modeling period, the cycle option is enabled. WEAP will wrap around from the end of the file back to the beginning. Select the cycle option. Finish. We see that we are using the cycle parameter. Do the same for the other three catchments. You must have these expressions for the humidity. Do the same for wind speed using the file wcatch. Remember to select the cycle option. You must have these expressions for wind speed. We are using the cycle parameter. Finally, do the same for the cloudiness fraction using the file n_n_catch. You must have these expressions for the cloudiness fraction. We are using the cycle parameter. The hydrological model is now ready to assign the hydrological parameters. WEAP has the default values assigned. We can run the model as it is. Go to the results view. Because we only have catchments and rivers, we only can explore results related to these elements. Select Supply and Resources, River, Streamflow. We already have simulated streamflow results. Before using the results, we need to calibrate and validate the model by adjusting the hydrological parameters. Go to the Data view. We could enter the hydrological parameters under the Land Use tab. However, controlling the parameters by using key assumptions adds flexibility to the hydrological model. In the O5 WEAP Basic Tools video tutorial, we saw what a key assumption is, how to create it, and link it to variables using the expression builder. In the theoretical section of hydrology, we saw that the parameters of the soil moisture method for the first bucket are assigned considering the catchment disaggregation, and the parameters for the second bucket are assigned for the entire catchment. That means that we need to create a structure for the key assumptions. We will create this structure. First, we need to add a hydrology category to group the key assumptions. Then we can add a key assumption for each parameter. Finally, we can add the disaggregation of the parameters, in this case by land cover classes. Open the Excel file Key Assumptions to see this structure. Go back to WEAP. Add a new key assumption and name it Hydrology. Right-click on the Key Assumptions category and select Add. Then type Hydrology. Add another one from the hydrology key assumption and name it F. Add the rest of the key assumptions from hydrology: KC, RRF, SW, C1, KS, C2, KD, and DW. Now add the land cover classes when is necessary. Start from the F key assumption. Copy the land cover class from the Excel file. Right-click on the F key assumption. Select Add. Right-click and select Paste. You will need to do this in every model depending on the disaggregation defined and how you want to assign the parameters. Sometimes you will need to repeat this same structure, aiming to regionalize the parameters if you have a large area. There is no fixed formula to create, assign, and adjust the hydrological parameters to calibrate and validate a WEAP model. You can create this kind of structure manually or by using a script. You can refer to the WEAP help for further information on the script editor. For tutorial purposes, the script was already developed and included within the model. Go to Area, Revert to Version, and select the Creating Key Assumptions version. This version has the model at the same state as before, but it includes the script. You could use this script as a template for creating key assumptions and modify it for your own interests. We will create the key assumption structure by running the script functions. Go to Advanced, Scripting, Run, Area Scripts, and select the script functions. It should start running. We see that the structure starts appearing. This script creates the defined key assumption structure for this model and assigns their initial values. You can modify it according to your own interests. It should run very fast. Once it finishes, we can check the structure created by the script. Collapse everything to explore the key assumptions created. Right-click on the panel and select Collapse All. Expand the Key Assumptions category. We can see that this structure is the same as the one we started to create manually. It has 9 parameters, 6 of them divided by land cover classes. The last step is linking the key assumptions to the hydrological parameters. In this case, we will control the hydrological parameters using key assumptions, and they will be global. That is, all catchments will have the same hydrological parameters. These may vary from model to model. Hydrological parameters should be defined for each catchment considering factors such as land cover, geology, and geomorphology. Select the east catchment. Go to the crop coefficient variable under the Land Use tab. We need to assign this parameter to each land cover class. Access the expression builder for the first land cover class. Go to the Branches tab. Then drag and drop the key assumption for this parameter. Go to the key assumption category. Expand it until you find the crop coefficient for the open spaces with little or no vegetation class. Drag and drop it into the editing box. Finish. WEAP adds an expression with the full path of the key assumption. This path corresponds to the location of the key assumption within the data tree. We can build these expressions in Excel and add them to the model. We will add all the expressions by exchanging data between WEAP and Excel. This is faster and easier than entering the expressions by using the expression builder. Go to Edit, Export Expressions to Excel. Select branches all, scenarios current accounts, variables all. It is not possible to specify more than one variable. We need to use the Excel filters. Okay. We can hide the columns we do not need. Hide the D, I, and J columns. In this file are the full paths for all the key assumptions. We need to sort the information in this file first. Select the third row and press the keys Ctrl plus Shift plus down arrow. You will select all the rows with information only. Then go to the Data menu and select Sort. Check the box next to My data has headers. Add 3 more levels. Select Sort by variable, then by level 2, then by level 3, then by level 4. We will start with the preferred flow direction. Now use the filter in the H column to only see that variable. Because the order of the variables in both files is the same, we can copy and paste the expressions. Continue with the crop coefficient parameter, Kc. Copy the expressions from this file and then paste them here. Do the same for the root zone conductivity, runoff resistance factor, soil water capacity, initial C1, initial C2, deep conductivity, finally, deep water capacity. Always double check that the order in both files is the same. We have finished assigning the key assumptions to control the hydrological parameters. Maximize this file to make sure that this is the active Excel file. Sheet 1, Sheet 1. In WEAP, go to Edit, Import Expressions from Excel. WEAP will import from Sheet 1, which is the active file. Yes. Following this process, we managed to link the key assumptions to the hydrological parameters for the 4 catchments. As you can see, exporting to and importing from Excel is faster and easier than using the expression builder to link each key assumption to each parameter. If we check, the key assumptions are linked in the parameters. If we go to each parameter, the key assumptions are linked. In Excel, there are many ways to create the structure of the expressions. You may want to use functions such as match, index, and concatenate. Now the hydrological model is complete. The river, catchments, runoff infiltration links, gauges were added. The areas, climate data, and hydrological parameters were assigned to each catchment. Go to the Results view for exploring the results. Go to Supply and Resources, River, Streamflow. When a streamflow gauge is added to a river, one reach corresponds to the observed streamflow. That reach can be recognized because it has the gauge word at the end. We will compare the observed streamflow, which is in the river reach marked with the number 5 and gauge, and the simulated streamflow, which is in the river reach with the same number. Select from the drop-down menu the Selected River Nodes and Reaches option. Choose the 2 river reaches marked with the same number, 5 and 5. Okay, this graph shows the observed versus simulated stream flow. It is used to evaluate the performance of the model. Models have a warm-up period, so it is suggested to exclude the results for the first year. We can export this data and calculate the goodness of fit metrics. You could use, for example, Excel, Python, or R. 7 results are extremely important when evaluating the performance of the hydrological model. The time series at the time step of the model of the observed versus simulated stream flow. The annual total of the observed versus simulated stream flow. The annual cycle of the observed versus simulated stream flow. We must exclude the years with no data. The flow duration curves of the observed versus simulated stream flow. We must exclude the years with no data as well. These 5 results are displayed at points where streamflow gauges were added in WEAP. The relative soil moisture 1 for each catchment. The relative soil moisture 2 for each catchment. The relative soil moisture graphs should show a stable behavior over time from a seasonal point of view, except for extreme conditions. Finally, the water balance, the land class inflows and outflows for each catchment. You should analyze these results to evaluate if the hydrological parameters assigned represent the water balance components properly. Save the version of your model. Go to Area, Save Version. Add the comment Hydrological Model Tutorial. If you go to the complete hydrologic model version of this model, you will see these charts saved as favorites. This version also serves for you to compare if you have done everything correctly. You can continue exploring the results of the hydrological model related to streamflow and catchments. In the next exercise, we will use the tool WEAP Model Inspector Tutorial. This tool can be used to calibrate and validate this model by exploring variations in the hydrographs and the goodness of fit metrics in response to changes in the hydrological parameters. We can vary the key assumption values that represent the hydrological parameters and evaluate the model performance for each set of parameters.